Hi, I'm delighted to be speaking to you today, but before I can do that, I need to share my screen with my PowerPoint slides. Here they are. And now I want to go to present a view and use the slideshow. And I'll minimize my face. So I was asked to talk to you today because my wife's work began in 1957 as a Dartmouth Freshman, when we were all freshmen when I took Introductory Psychology. And since then, I and my collaborators have made a series of discoveries right up to the present day. This work is about how each brain makes a mind. One discovery is a proposed scientific solution of the mind-body problem, which asks how, where in our brains, and why, from a deep computational perspective. We're conscious. In particular, we can consciously see, hear, feel, and know things about our unique experiences and use our conscious states to plan and act to achieve valued goals. My recently published magnum opus provides a self-contained and non-technical overview of my discoveries during the past 65 years with over 100 gifted PhD students and postdocs. The book also provides principled explanations of experiments by hundreds of psychologists and neuroscientists about many aspects of how our minds work. Moreover, you don't need to know any science to read it. In fact, friends of ours who include a rabbi, a pastor, a visual artist, a gallery owner, a social worker, and a lawyer have enjoyed reading it. The book is called Conscious Mind, Resonant Brain, How Each Brain Makes a Mind. Just so you know, I'm not a crank selling snake oil to fix your mind. I blush to say it, but as early as 1989, the president of Boston University, John Silber, a notoriously tough guy, introduced me as the Newton and Einstein of the mind to a Boston area audience when I was about to give the annual university lecture. And I'm gratified to say that some reviewers of my magnum opus wrote the same thing. The topics explained in my magnum opus include how we see and hear, consciousness, attention, learning, recognition, cognition, emotion, speech and language, decision-making, how we time things, how we plan things, how we predict things, how we navigate, how we act with our eyes, legs, and arms, many aspects of how our daily lives are controlled by our brains. And I show, moreover, that brain mechanisms are a special case of a universal developmental code that's shared by all cellular organisms, not only brains. And these explanations clarify when things go wrong, how behavioral symptoms can occur during mental disorders that afflict millions of people, including Alzheimer's disease, autism, amnesia, schizophrenia, post-traumatic stress disorder, attention deficit hyperactivity disorder, visual and auditory agnosia and neglect, and disorders of slow-wave sleep. The book also clarifies biological bases of aspects of the human condition, including creativity, morality, religion, how we understand when things cause other things, as well as explanations of how bad things can happen, superstitious, irrational, self-defeating, and even self-punitive beliefs and behaviors, and how they can persist in certain social environments despite disconfirming evidence, as we see all too tragically today. One final note, I subsidized the book's cost with my own funds, although it's almost 800 double column pages long with over 600 color figures, because I try to explain so many things. Because of my subsidy, the hard copy costs only $33 on Amazon, and the Kindle version costs only $19. Oxford University Press, that published the book, charges $35. I did it so everyone interested in how our brains work can hopefully afford to buy my book, including retired people like us. So let's return to the work I did as a college freshman. I was fascinated by how do we learn and remember lists of items or events, or how do we learn the temporal order of events? The events may be letters, grocery items, baseball scores, routes from your bedroom to the bathroom. Even how do we even learn the alphabet, ABC up to XYZ, by practicing it over and over again? This is more generally called the problem of serial order and behavior by the great American psychologist Carl Ashley, who wrote in 1951, "It's the most complex type of behavior that I know, the logical and orderly arrangement of thought and action." And after Lashley, there were other great American psychologists, including Clark Hull, Carl Hovland, Benton Underwood, who also contributed to understanding serial order in behavior. So if we ask, how do we learn and remember lists of items or events? Well, one way is to use what's called serial verbal learning. And what happens here is, let's say you're sitting in front of a box that has a window in it. And let's say the alphabet's going to go through one letter at a time. Let's say when A is in the window, you have to predict B, which you can do if you practice it on multiple trials. Then when B is in the window, you have to predict C, and so on. And you do this over and over again until you can make all the correct predictions of the next letter several times without error. And so the idea is you'll have A, B, C coming at a certain rate. Let's say this rate is called the intra-trial interval, little w, because a trial is one presentation of the alphabet. And then there's an intertrial interval, big W, which is just how much you rest between successive occurrences. So you practice, you rest, you practice, you rest, until practice makes perfect. Well, a basic issue here is, where is the end of the list? You know, if you keep repeating the list over and over again, if the intertrial interval equal the intratrial interval, it would just be basically a blur. So the amount of rest helps to partition each presentation of the list. But another way of saying it is the non-occurrence of a letter, the intratrial interval times after Z is presented, defines the end of the list. This intertrial interval, which is bigger than the intratrial interval, the rest interval, is what enables us to learn the list. And the remarkable fact here is that a list's middle is harder to learn than its beginning or end. If you count how many errors are made at each list position until you learn it, there are more errors in the middle than the beginning or at the end. For example, during alphabet learning, you'll make more errors when you learn that N follows M in the middle than when B follows A at the beginning or Z follows Y at the end. During daily life, for example, you may remember how a relationship began or ended, but the middle is a muddle. So it's harder to learn in the list middle than its beginning or end. And this is really paradoxical. And I want to clarify why. Because if the past influenced the future, but not conversely, there would be more response interference as you get deeper and deeper into the list due to the presentation of more preceding items that could interfere with your learning. So you should have an increasing number of errors as you get deeper into the list, because it's harder and harder. But what actually happens is what's called the Bode serial position curve, where the beginning and the end of the list have fewer errors and the most errors are near the middle of the list. And in fact, explaining the Bode serial position curve was considered an intractable problem when I first considered it as a freshman. Moreover, let's say you're presenting items every 2 seconds and you rest for 6 seconds between presentations, then this will be the number of errors you make. But if you present the items every 2 seconds and rest longer between presentations, like 2 minutes and 6 seconds, then there are many fewer errors. And this is one sense in which events can influence each other backwards in time, because the size of the intertrial interval W influences how many errors occur throughout the list items that have already occurred. It's in this sense that the non-occurrence of future items influences how we learn past items. And that excited me a lot when I was a kid. Moreover, if, let's say, you present the items with an intratrial interval of 4 seconds, so they occur with a little bit of spacing between them, then the errors collapse significantly throughout the list. And here is a summary of some data of Hovland showing when you have a fast presentation rate and a relatively short rest, you get quite a lot of errors. If you still have a fast presentation rate and you rest longer, the errors collapse somewhat. But if you have a slow presentation rate, no matter how much you rest, there aren't that many errors. Moreover, the bow is skewed. It's the place where it's hardest to learn is nearer to the end than the beginning. And I was wondering, why does this happen? And it happens because future associations are stronger than past associations. And backward learning, as I'll show you in a moment, clarifies why this happens. So the point is that if you practice a list AB, then you'll also find you've also learned the reverse list BA. However, if you practice A and then B, and presumably you're also beginning to learn BA automatically, you'll eventually be able to learn ABC if you present that later, which shows that when C occurs, the future association from B to C must have been stronger than the backward association from B to A, or you couldn't even learn the alphabet. And backward learning also explains error gradients. So at the list beginning, there are anticipatory errors. If you try to learn AB, you might also make the mistake AC or AD, but with less probability. At the list end, they're perseverative. If you try to learn YZ, you might also learn YXA backwardly. And in the list middle, because there are a lot of items that have been happening, you might make anticipatory and perseverative errors. And these data forced me to realize that our brains contain neural networks, because I was led to say there are inputs coming in. They'll activate a population corresponding to A and B, and then signals will go from A to B and from B to A, and there'll be associations that'll learn the list from A to B and from B to A. You also need competition for this to work properly. This is a kind of divisive competition that normalizes the activities of competing cells. It just turns out that's how cells compete. And that explains why, for example, you have the bow, because you have more cells that are active in the middle, and by normalization, you'll get weaker associations. So this 1957 discovery is an early example how a psychological analysis of learning can lead to insights about how our brains make our minds. Otherwise expressed, brain evolution needs to achieve behavioral success. And that's why I call my book Conscious Mind, Resonant Brain, How Each Brain Makes a Mind. Thanks very much for listening.